What is statistics? Statistics is a field of study where statistics is a group of methods that are used to collect, organize, present, analyze, and interpret data to make decisions. Basically, it is a field of study which collects data and interprets it to make decisions. Collection refers to the gathering of information or data. Organization or presentation involves summarizing data or information in textual, graphical, or tabular forms. So, information can be represented in text, in graphs, or in tabular forms. And analysis involves describing the data by using statistical methods and procedures. So, if we apply analysis on the data, we can do it by applying statistical and mathematical procedures. Interpretation refers to the process of making conclusions based on the analyzed data. So after analysis, we do the interpretation of the data that helps us make better business decisions. What are the types of statistics? First is descriptive statistics, and the second one is inferential statistics. We'll see what they are now. Descriptive statistics deals with how we characterize and make groups of data based on certain properties of that data or subset of data. So the definition is it is a statistical procedure concerned with describing the characteristics and properties of a group of persons, places or things. So this involves gathering and organizing, presenting and describing data. For example, we may describe a collection of persons by stating how many are poor and how many are rich, how many are literate and how many are illiterate, how many fall into various categories of age, height, civil status, IQ, and many more. So basically, descriptive statistics defines data by their attributes or properties. Next, we move on to inferential statistics. So what is that? It is a statistical procedure that is used to draw inferences or information about the properties or characteristics of a large group of people, places, or things on the basis of the information obtained from a small portion of that large group. So basically, if we have a superset of data, we can take a small set of that or subset of that data and analyze it and make interpretation or inferences on that based on that subset and apply it to the whole group or superset of that subset. So basically we inference about the population or superset based on a small subset, and this is also known as inductive reasoning or inductive statistics. So the example for this can be if we have a geographical area, we not take individual responses out of each of those persons living in that full or whole geographical area. We may take a small subset of those people living in that geographical area and take their living habits and apply that to the whole geographical area. So all the people might be having the same type of living habits based on that subset data. Hope this is clear. Population versus sample. In the previous slide, I talked about the term population. That is basically a superset or main set of data. That is the full data that we have in hand or that can be considered. And whereas sample would be a subset of that data. So in statistical studies, mostly we deal with samples and not population because samples give rough idea and sometimes not even rough, accurate prediction about the entire population. If we take the data about the sample and run analysis on it, we will get the entire population's analysis. So what is population definition? A population consists of all elements, individuals, items or objects whose characteristics are being studied. The population being studied is called the target population. So hope this is clear. It consists of all individuals, items or objects whose characteristics are being studied. It is the entire superset of that. And the population is also known as the target population in this case. And what is sample? A portion of the population selected for study is referred to as a sample. That is a subset of the population. Other key statistical terms. Variable is a characteristic or property of a population or sample which makes the members different from each other. So just like parameters in case of the pandas data frame we discussed earlier, where each column represents a specific property of that data set, we have a variable in statistical terms, which implies that it is a characteristic or property of a population or sample, whatever you take, I mean, what a sample or population, which makes the members different from each other, classifies them in fact. And what is constant? It is a property or characteristic of a population or sample which makes the members of the group similar to each other. So constant may be, suppose if we take gender, and all if all the people in the group are males, then it implies that gender is constant. So it implies that constant will be same for all the rows of the data of the population or sample. Data. What is data? Data are numbers or measurements that are collected as a result from observation, interview, questionnaire, experimentation, test, and so forth. Hope this is clear. The singular form of data is datum. Now we'll study an important concept of how decision trees are made. So suppose we need to make a decision tree for the following data. This is the table here, and we will discuss the maths behind how decision trees are made. That is, how each node is selected at each point of division. We will discuss information gain and entropy and Gini impurity and Gini gain. So suppose we have this table here, and it defines the variables are outlook, temperature, humidity, and wind, and they have different values here in the table. Outlook can be sunny, overcast, rain. Temperature can be hot, mild, and cool. Humidity can be high, normal, and wind can be weak and strong. So based on these parameters, we need to decide whether it is suitable to play football or not. So this is the dependent variable. That is the final output that is required. So here there are four independent variables to determine the dependent variable, which are outlook, temperature, humidity, and wind. The independent variables are given here, and the dependent variable is whether to play football or not. So this is the same table here. We need to find which variable should we take as our root node in the tree first, and this will lay a benchmark of how we select further nodes at each point of division. So for that we find the total entropy at the root level, which is the current scenario. Current scenario is the full table here. So you find the total entropy for this system. There are in total 14 cases or 14 rows here. You can count from here to here, and number of yes are 9 and number of no's are 5. So therefore, given the entropy formula as Hx is equal to minus summation I is equal to 1 to n pxi log b bxi, basically here b is always 2, and it is taken to the base 2, I mean. So we calculate entropy of the system as minus 9 by 14 log 9 by 14 plus 5 by 14 log 5 by 14, which is equal to 0.94. So basically what's happening is, this is the probability of yes 9 by 14, that is 9 yes out of 14 total cases, and log of pxi, that is log 9 by 14 again, and it is a summation here, so we have to take this no class as well here. Its probability will also be taken, so 5 by 14 log 5 by 14, and all in minus, so it will be 0.94. So this is the base class or class S's entropy. So this is the main entropy at current situation. Next, we can take the root node to be either outlook, temperature, humidity, or wind and divide based on that. So what we'll see what will happen if we take the root node as outlook parameter first, and similarly we will calculate for temperature, humidity, and wind what happens. So if we take outlook as the root node, we have to calculate the entropy for outlook for the system after we take outlook as the node. So this is given as entropy ES outlook here. I'll tell you how it is calculated now. So from the table on the left, we can deduce the conditions of outlook as below table. So this is a table here. If we take outlook only, outlook can be sunny, overcast, and rainy. So for sunny there are 3 yes and 2 no's and total is 5. For overcast there are 4 yes, 0 no's and total 4 instances, and similarly for rainy it is 2 and 3 and 5, total 14. For outlook is the number here. So outlook is in 14 cases. I mean it is basically the total number of rows in the main table. So what we need to calculate is average weighted entropy. That is, we need to find the total of weights of each feature multiplied by probabilities. So given a weight for sunny will be here 5 by 14, since this is 5 here, so we will take it as 5 by 14. That will be weight of sunny feature. Similarly for overcast feature the weight will be 4 by 14, and for rainy it will be 5 by 14. So that will be weights of each feature and multiplied by probabilities here. Probabilities is the same as that, like that we calculated earlier. So probability of yes for sunny will be 3 by 5, and probability of no will be 2 by 5. So the average weighted entropy for outlook is calculated on the basis of each of the entropies of sunny, overcast, and rainy parameters as below. ES outlook is equal to 5 by 14 into E3 by 2, that is for sunny. Here it is calculating from here to here, and from here to here it is 4 by 14 into E40 is for overcast. E40 simply implies the entropy for overcast on yes and no classes, and 5 by 14 into E2 by 3 is for rainy. This is the weight 5 by 14 for rainy, and E2 by 3 is entropy for rainy. So that turns out to be 5 by 14 into, from the entropy formula, minus of here 3 by 5 into log 3 by 5 minus 2 by 5 again into log 2 by 5. Similarly 4 by 14 into 0, since that will turn out to be that logarithm will turn out to be 0. It's written here 0. Next 5 by 14 plus 2 into 2 by 5 log 2 by 5 minus 3 by 5 log 3 by 5. That turns out to be finally 0.693. So this is how we calculate the entropy of outlook in total, by giving weighted average to all the entropies of its features. Hope this is clear. The next step is to find the information gain. It is the difference between parent entropy and average weighted entropy we found before. So information gain for outlook node will be 0.94, as 0.94 was the entropy of the whole system when we calculated earlier. and minus 0.693 that we have just calculated, that is 0.247. So we have calculated the information gain for Outlook here. Similarly, we find the information gain for temperature, humidity and windy features to be selected as root node, and we get these values. So the highest one will be Outlook here only. So we take Outlook as the root node since information gain for Outlook feature is the highest. So if we select Outlook as our main root feature, our data looks like this here. So basically it is divided into sunny, overcast and rain divisions, and Outlook is based on Outlook, I mean. And so since overcast has only all yes here, so it can be deduced that if it is our Outlook is overcast, we can play football. So that means if Outlook is overcast, football will be played, and our decision tree looks as this here. Main node is Outlook here. Sunny and rain are still to be decided, and if it is overcast, it is a yes. As you can see, for sunny there are 3 no's and 2 yes, and for rain it is 3 yes and 2 no's here. So based on further divisions, we will decide what nodes we need to select based on entropy of the further features. So we will see next how it is done. Basically it is done on the same benchmark that we how we deduced for Outlook and made it stand against temperature, humidity and wind. Same feature division we will do again. So in the same way, next step is to find the next node in our decision tree. We have to determine which of the following temperature, humidity or wind has the higher information gain. So for Outlook being sunny, we will take the case first. So parent entropy of E sunny will be 3 no's and 2 yes. So minus 3 by 5 log 3 by 5 minus 2 by 5 log 2 by 5, that is 0.971. Now we calculate the information gain of temperature, and next after that we'll calculate for humidity and then wind for Outlook being sunny case. So we deduce E sunny temperature as this much because temperature table can be like this based on above data. If temperature is hot, there is 0 yes and 2 no's, total is 2. Similarly for cool and mild, this is the data, total is 5. And so E sunny temperature will be 2 by 5 into E02, that is entropy of yes and no for temperature, and no for hot, I am sorry, hot, and for E11 would be for cool temperature, and E10 would be entropy for mild temperature. So this is the weights. 1 by 5 is the weight for mild, 2 by 5 is the weight for cool, and 2 by 5 again is the weight for hot. Similarly, we calculate the E entropy for the weighted entropy for entire temperature feature. That will comes out to be 0.4 after calculations. Now we calculate the information gain. So information gain for sunny and temperature will be again entropy of sunny minus entropy of sunny temperature, that is 0.971 minus 0.4, that is equal to 0.571. Similarly for humidity and windy we get these. So out of these, for humidity it is the highest here. So we take humidity as a node that comes under sunny. Okay, so Next we have this table where humidity is given high and normal, and from this table we can say that play will occur if humidity is normal and will not occur if it is high. So this is simple. If humidity is high, it is a yes is 0 and no is 3. All instances are no, and here also all instances are yes if normal is humidity is normal, I mean. So we can directly make the final output leaf for this case. Similarly, we find the nodes under any, and a branch with entropy more than 0 needs further splitting. So entropy of 0 is the best. That means there is no need for further splitting, but if greater than 0, then we require splitting. So I have told you, the more the information gain and the better the splitting, and the lesser the entropy, the better the splitting. Okay. Finally, our decision tree will look as below. So first is outlook, and then sunny and rain will be other features. And basically, this is the final decision tree. That is that will give us yes and no uh, and cases. Classifying using Gini impurity and Gini gain. The same decision tree can be classified using Gini impurity and Gini gain methodology. So instead of information gain term, we use Gini gain, and instead of entropy, we use Gini impurity values. The concept stays the same. So Gini of E is equal to 1 minus summation j is equal to 1 to c pj square. I'll discuss what is this in coming slide. As the first step, this is the same table here as earlier. So in the first step will be to find the root node of our decision tree. For that, we'll calculate the Gini index of the entire set first. So Gini of this set is 1 minus number of nodes, that is 1 minus summation pi square, that is probability of each of the class, that is yes and no. So for yes it is 9 by 14 and no is 5 by 14, so pi square, so whole square is here in each case. So 1 minus pi square will be Gini impurity. So as the next step, we will calculate the Gini gain. For that, we will find the average weighted Gini impurity of each of these features: outlook, temperature, humidity, and wind. For each of these, we will find the Gini impurity. Let's see how it is done. First, we consider the case of outlook. So outlook can be sunny, overcast, rainy, and all these table we have seen earlier as well in the case of outlook from the main table. So Gini for S outlook will be the weighted average into weighted average of sunny into Gini of sunny plus weighted average of overcast into Gini of overcast plus weighted average of rainy into Gini of rainy. So it can be calculated as 5 by 14 into 1 minus 3 by 5 whole square, since there are 3 yes here and 2 no's. So 3 by 5 minus 2 by 5 whole square whole square. Similarly others. So it comes out to be 0.342. So Gini gain for outlook. So Gini, what is Gini gain? Gini gain will be similarly similar to information gain, where we subtract the impurity from the parent node. So parent node Gini was impurity was 0.459 and here it is 0.342. So we subtract it from that to get 0.117. So this is Gini gain. Similarly, we calculate Gini gain for temperature, humidity, and windy. So still we find that our Gini gain for outlook is the maximum. So we'll take outlook as the root node. So classifying using Gini impurity and Gini gain finally concludes with we have to choose the feature that has the highest Gini gain, and Gini gain is higher for outlook, so we can choose it as our root node as discussed earlier. Proceeding in similar fashion as in the case of entropy and information gain example, we can finally achieve the same decision tree as before. So it is the same method, we just need to change the formulas. But why we use Gini impurity and Gini gain is it is computationally more efficient because the log term is not involved. Logarithmic term is involved in entropy, and it is computationally more not effective. So, but in Gini impurity we have the square term. So Gini impurity is computationally more effective. And finally, I'd like to conclude by saying that decision trees are mostly used in binary classification, but we can use it for other classification, regular classification as well, by selecting the appropriate formula, by rewriting the formula. So suppose we have the formula of Gini impurity as 1 minus summation, sorry, I is equal to 1 to n, each of the feature set probability in a class pk. So this k is also is our uh, number of values that the dependent variable can take. So the formula will be pk 1 minus pk square. So we took for yes and no, but if we need to take for other values, we can take that for other values as well, and take the weighted average and use accordingly in our formula. Hope this is clear.